Today I'm going to talk about parallel lines and planes. First, I'd like to talk about images under compositions. Mappings, remember, are done in the reverse order as listed. So as you look at this, it says R composed with S. S goes first and then R goes second. So if we let A be a set and R and S be relations on A, then for any subset B of A, R composed with S of B, notice these double quote marks indicate that B is a set, we can nest them together like this. S of B and then R of that result. The parallel postulate says for each line L and each point P, there's exactly one line K such that P is an element of K and K is parallel to L. So let me draw a picture of what that would look like. So I have a line L and then I have a point P. What this says is there's only one line that's parallel to L that will go through that point P, and that is the line K. Now I'd like you to pause your video and do exercise 189. When you are ready for the answer, press play again. Okay, here's the answer to exercise 189. I'm going to read through it. Let pi be a plane. Complete the following proof that parallelism of lines in pi is transitive. That is for all lines L, M, and N in pi. If L is parallel to M and M is parallel to N, then L is parallel to N. And if we draw a picture of that, it's easier to see that this would be true. If I have L parallel to M, this is how I mark lines parallel, and I know M is then parallel to N, then it should be easy to see that L then must be parallel to N. Again, that's the transitive property for parallelism. So here's our proof. Let pi be a plane and let L, M, and N be lines in pi such that L is parallel to M and M is parallel to N. Suppose we're going to try a contradiction sort of proof. Suppose that L is not parallel to N. Then it is not the case that either L is equal to N or L intersects. Let's say that again. It's not the case that either L is equal to N, in other words, they're the same line, or that L and N don't intersect. Remember that a parallel lines that are parallel are either the same line or they never intersect. So we're going to say that's not the case. And so from exercise 59, they must intersect in exactly one point, say P. So if lines intersect, they intersect in exactly one point. But then we have two distinct lines, L and N, that pass through P and are parallel to M. But this contradicts the parallelism postulate that says through any one point, there's exactly one line that's parallel to another. But then we have two distinct lines, L and N, that pass through P and are parallel to M. Since this contradicts the parallelism postulate, we conclude that L is parallel to N. And that proves the parallelism transitive property. Now I'd like you to press pause on your video and try exercise 190, where we are trying to complete the proof that if L is parallel to M and L is not parallel to N, then we can conclude that M is not parallel to N. So pause your video. When you're ready for the answer, press play again. So here's the answer. First, I'm going to draw it just to show that it makes sense. If I have a line L, and that is parallel to M, and I have another line that is not parallel to L, let's draw it like this, and that's N, I should then be able to conclude that M is not parallel to L. And you can see from my picture that that would be the case. So now let's go through the proof. Let pi be a plane and let L, M, and N be lines in pi such that L is parallel to M and L is not parallel to N. Suppose further that M is parallel to N. So we're going to try to work this through by contradiction. Then by exercise 189, we obtain L is parallel to N, but this contradicts our assumption. Hence, M and N are not parallel. Now I'd like you to try exercise 191. It says let L, M, and N be lines in the plane pi. Complete the following proof that if L is parallel to M and L is perpendicular to N, then M is perpendicular to N. Press pause when you're ready for the answer again. Press play. So first I'm going to draw myself a picture so that I can see that this makes sense. So I have L, M, and N. They're lines in my plane. And I have L that is parallel to M. And I have L that's perpendicular to N. So these are parallel. At that point, I want to conclude that M must then be perpendicular to N. And of course, from the picture, we should see that that's the case. Remember that corresponding angles are congruent. These are corresponding angles. So let's read through this. Let pi be a plane and let L, M, and N be lines in pi such that L is parallel to M and L is perpendicular to N. Suppose further that M is not perpendicular to N. So remember, we're looking at this, we're going to try to prove this by contradiction. Now, L is perpendicular to N, and so it is plain that L is not parallel to N. Thus, by exercise 190, M is not parallel to N. So these two lines must intersect in exactly one point, say Q. Since L is perpendicular to N, we have that the image of L is equal to L. So that's the case because if I know that L is perpendicular to N, L is a fixed figure in the line reflection over N. And since M is not perpendicular to N, we have that the image of M, when I reflect it over N, is not equal to M. Now, by one of our assumptions and the fact that reflections of lines preserve parallelism, we obtain this result, that if I know L and M are parallel from the beginning, and then I reflect them both over the same line, their images should be parallel to each other. So the reflection of L should be parallel to the reflection of M. Hence, by 1 and 3, we obtain this result. The reflection over N of L is equal to L itself. L should be parallel to the image of M. Now, Q is an element of N here. And so the reflection of Q is equal to Q because I'm reflecting it over the line that it's on. Also, Q is an element of M, and hence Q is an element of my reflection over line N of M. Thus, Q is an element of the intersection of M and the reflection of M. From 4, I believe this is 4 here, from 4, one of our assumptions, 2 and 3, we obtain a contradiction to the parallelism postulate. Through one point, there exists exactly one line that's parallel. Thus, M must be perpendicular to N. Now, I'd like you to press pause again in a moment. We're going to complete the following proof that the parallelism over relation in pi is an equivalence relation on the set of all lines of pi. So press pause on your video, complete the proof, and then we'll discuss the answers. Here's the answer. Let pi be a plane. Complete the following proof that the parallel relation is an equivalence relation. Remember, equivalence relations are reflexive, symmetric, and transitive. So we have to prove each. In the set of all lines of pi, let L be an element of the set of all lines of the plane pi. Then L is equal to L. So L is parallel to L, and thus L comma L is an element of the parallelism relationship, and so the parallelism relation is reflexive on the set of all lines of the plane. Now I need to see that it's symmetric. Let L, M be elements of the set of all lines of a plane, be such that L is parallel to M. So if that's the case, if that's true, I have two cases. L is equal to M. Well, if they're equal, then they're parallel to each other. In case 2, L does not intersect M at all. So the intersection of L and M is the empty set. Then, because intersection is commutative, I know that M intersect L is also empty set. Therefore, the lines are parallel. So, symmetric property. So, symmetric means I can change the order. So, if L is parallel to M, M must be parallel to L. Transitive, I need to prove next. So, I let the L, M, and N be lines of the plane, be such that L is parallel to M and M is parallel to N. So I have to then show that L is parallel to N to show that it's transitive. Then by exercise 189, L is parallel to N. Thus, the parallelism relationship is an equivalence relation on the set of all lines.